So welcome to the master class. The goal of the master class, to my mind, is somehow to introduce some ideas which join geometry and algebra. And in QGM and in our department, kind of we have both. But my general feeling is that so far these directions were, if not unrelated, then not joined enough. And geometric representation theory, which is the general trend of the coming masterclass, is an area where these two directions are united, and for bonus of both. So welcome to lectures of Ivan Losev and Jose Cimental Rodriguez from Northeastern University, not to mix with Northwestern University.
Thank you. You'll be surprised, but there are also Southeastern and Southwestern.
Do you claim that there's a Western Pole and Eastern Pole as well? You know,
no.
Winnie the Pooh once discovered one of them. Anyways, so I know the general level of local students, so it was decided that the introduction will be very mild, and the general technique of symplectic geometry, symplectic reduction, and related topics will be introduced, and then Quiver varieties and their quantizations will be discussed. And this is extremely popular and important subject, which indeed is the frontier of modern mathematics, and I hope that we'll learn more about that in this week. So welcome again, and let's start. So first lecture is by Jose.
Okay. Thank you. Well, first of all, thank you for this wonderful opportunity. And as Sergey said, the introduction will be, well, we have to define what a quiver variety is, and in order to do that, first we have to introduce GIT, which stands for geometric invariant theory. So the plan for this first lecture is first I'm going to introduce so-called categorical quotients. Then I'm going to introduce a finer type of quotient, which is a GIT quotient. And finally, I'm going to see these two, well, precisely this, in the case of quivers. Okay? So this is the plan for the next 45 minutes. And let me specify that the base field will always be field of complex numbers. And well, I'll start with a reductive group, well, reductive algebraic group G. Recall that this means that every rational representation is completely reducible. And let's say that, well, for example, you can take G to be a product of GLNs. Okay? And let's say that G acts on an affine algebraic variety. And, well, we want a space parametrizing the orbits. Okay? Well, the first idea is to look at the invariant functions, which, well, these are all the regular functions that are invariant under the action of G. And well, let's see what type of variety this defines. First of all, well, it's not such a bad idea to look at this guy. We have a theorem which is very classical. It's essentially due to Hilbert. And this theorem says, well, first of all, the algebra of invariants is a finitely generated algebra. So that's good. So we can look at its spectrum, which we're going to denote by x/g. Well, since this is a subalgebra of C of x, we have a map, let's say pi, from x to x modulo g. And well, this is surjective, and every fiber contains a unique closed orbit. And part 3 of this theorem says that if you have y containing x, a closed G-stable subvariety, then the induced map from y modulo g to x modulo g is a closed embedding. Okay. An important consequence of this theorem, whose proof, well, I don't know if you know Ivan, but his favorite word is exercise. So the proof of this corollary is an exercise. The closure of every orbit in X contains a unique closed orbit. And well, the proof, exercise. Okay? And just as a matter of notation, we're going to call this variety the categorical quotient of x by g. Okay? And, well, it receives its name categorical because if you have a map, let's say from x to C that it is G invariant, then it factors through the categorical quotient. And this is by definition. Okay? Now, thanks to this, here this tells us that the closure of every orbit in X contains a unique closed orbit. So we would like to have a way to identify that closed orbit. Okay? This is done following theorem, which is called the Hilbert-Mumford criterion. And this says that, okay, so let the orbit of y be the unique closed orbit containing the closure of the orbit of, let's say, x. Then we can have one parametric subgroup, which is nothing else but an algebraic group map from C times to G. there exists an algebraic group map from C times to G. This is also known as a one-parametric subgroup. Such that the limit when t goes to 0 of gamma of t applied to x is in this closed orbit. Okay, so we can always approach the closed orbit using an appropriate one-parametric subgroup. Okay, let me give an example of all of this. An easy example. So let G be C times acting on C to the n by dilation, so t applied to x is just t to the minus 1 x. Well, and here we have that the algebra of invariance is just C. And so the quotient is a single point, which basically says that this action has a unique closed orbit, which is the orbit of 0. Okay. And this is not what we would like to have for this quotient. I mean, geometrically, we would like to have something like p to the n minus 1, right? So in some cases, this quotient is, well, pretty much useless, such as this case. And to remedy that, we introduce GIT quotients. But before that, any questions?
Can you say again this comment why it's categorical quotient?
Oh, if you have, say, a map from X to C, which is G invariant, then it factors through the quotient. So it satisfies some universal property.
Just to make it precise, write it on the level of algebras, and then everything will be clear.
Okay. So let's say
Z is affine.
So you have from C of x, then since it is G invariant, well, its image has to be contained actually in the invariance. Okay? So the image of this map has to be contained here. This is what this is saying.
Have just identity map, it means that quotient is embedded into X itself?
But the quotient is not G invariant. I'm sorry, the identity map is not G invariant. I don't know if that is different.
Right, okay.
Yeah. Okay? Okay.
G invariant means constant on C invariant.
Yes. Okay? Yeah. Any other questions? Okay. So let's go to GIT quotients, which is some sort of better quotient, but there is a price to pay. This is going to depend on a parameter, which is a character. It's a character which is an algebraic group map from G to C times. Okay? And now we are going to relax the condition of being invariant, and we are going to define what a semi-invariant function is. F is and theta semi-invariant if, well, now we have f of g to the minus 1x. This is not going to be f of x, but it's going to be f of x multiplied by an appropriate scalar, which is theta of g to the n times f of x. Okay? Sorry? Oh. Thank you. F is a regular function. So again, we have g acting on an affine variety x. Thank you. Okay. We have again g acting on an affine variety x. So we can take a function on x, and this is the definition of it being semi-invariant. Okay. We don't ask it to be invariant under the action of g, but we ask it to be multiplied by a character. And, well, let me denote by c of x, g, and theta. This is going to be the n theta semi-invariant. Functions. I guess these are the erasers. Okay. Now a point an element x in x is said to be semi-stable, well, theta semi-stable, if there exists a positive number n and an n theta semi-invariant function such that f of x is non-zero. Okay. In other words, we define the locus of theta semi-stable points to be the union of all the non-vanishing locus of semi-invariant functions with positive n. Okay. But let me give a more intrinsic notion of a point being semi-invariant that, well, in particular, it does not depend on finding a function f.
Excuse me, what do you mean by fx different from 0?
Well, f is a map from x to c, right?
Or for some x, what do you mean?
No. So you fix an x, okay?
Fix an x.
And then
Yeah.
you want to say that it is.
You have fixed x.
Yeah. Okay. 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 So let me give a more intrinsic characterization of semi-stable points. So the locus of semi-stable points is well, before saying this, let me first consider another action. So let G act on x cross C. I will. G applied to xc is G applied to x and theta of G times C. Okay? Remember that this is just a complex number. Then point X is semi-stable if and only if, well, you have G. Take the orbit of x, 1 under the action of G on this variety. Close it. Well, you want for there not to be points whose second coordinate is 0. Okay? And well, thanks to the Hilbert-Mumford criterion, this happens if and only if there doesn't exist a one-parametric subgroup let's say gamma of t, such that the limit when t goes to 0 of gamma of t applied to x exists, and theta of gamma of t is t to the m with positive n. So all the characters of c times are t to the some power, and if we want this limit to be 0, then the power has to be positive. Okay? And the proof is Ivan's favorite board exercise. Okay? Now we can define the GIT quotient. So,
Will you give an example when you come to the end of this topic?
yes, yes. So note that if we defined well, let me not give it a name. We can do the sum of all the n theta semi-stable functions. Okay. Well, this is a graded algebra. Meaning that if you multiply two functions, then these things are going to add. Okay? And, well, we define the GIT quotient x by g depending on theta to be, well, the prop of this graded algebra. And I'm going to say a bit more geometrically how to construct this guy. Okay.
I know this is stupid, but can you write in one line the calculation which shows it's an algebra
Okay. So what we have to show here is that if, let's say, if 1 is n1 theta semi-stable, and if 2 then the product do you want me to show this? So let's take a point x and x, and f1 times f2 g inverse x. Well, this is the product. Now here, theta of g to the n1 comes out, and there theta of g to the n2 comes out. And well, yes, okay. So this is really a graded algebra. And let me just say in a bit more geometric way how to construct that. Well, let's take, for example, a semi-invariant function. And note that its non-vanishing locus is this table. Okay? And so we can form the categorical quotient. Okay? And now, well, the GIT quotient is obtained by gluing these quotients. Well, but I need to tell you how to glue along xf1 quotient g and xf2 quotient g. Well, the intersection should be
X of f is just non-zero support of f.
Oh, yeah, this is the points where f does not vanish. Yes. So the intersection of these two guys inside the GIT quotient well, this should be the categorical quotient of xf1, f2. Okay? Well, and this is considered inside the GIT quotient.
Just a little remark. So the description has nothing to do with GIT. It's just how you define projective varieties, like as projects of something.
Now, that description lies as well. We have a map from the semi-stable locus to the GIT quotient. Okay? Well, precisely because of this description, this map is affine. Okay? Another observation is that, well, the 0-degree component there is just the algebra of invariance. Okay? And so we have a projective morphism from the GIT quotient to the categorical quotient. Okay? In such a way that the following diagram commutes. So we have the semi-stable locus is included in X. Then we can map X to the quotient and the semi-stable locus to the GIT quotient. now we have this map. Well, this map commutes. Okay? This diagram, sorry, commutes. Any questions?
Time for an example.
Yes. Now it's time for an example. So let me go back to the example we had before. So again, remember we had G is C times acting on C to the n. Okay, and remember that the GIT quotient depends on a character, so let me take the simplest character, theta of t is t. Okay? Then well, the n theta 7 invariant functions, these are the homogeneous polynomials when you take a basis of degree n. And let me just remark that here I take c of x to be I'm using n too much. So. Okay? Yes?
So we take projective space as a special case, the common projective space where you have the homogeneous polynomials.
Yes. Yes. I mean,
it's a special case for that.
For this GIT quotient. Yes. Yes. For this theta, then you have that precisely. GIT quotient is the projective space. Yes. Okay. But what happens if you take, let's say, theta of t is now t to the minus 1? Then, well, we can check that actually the semi-stable locus here is empty. Okay, so the GIT quotient is empty.
So what was the semi-stable locus for the previous character?
For the previous character, the semi-stable locus is everything minus 0. Okay.
Why?
Why? Well, let's say that, well, first of all, it's clear that every homogeneous polynomial of positive degree vanishes at 0. And if you have a non-zero point, well, you can find an homogeneous polynomial of positive degree which does not vanish there.
If you try hard, you're going to find a polynomial of positive degree equal to 1.
Yeah. Yeah. Okay. Okay. Any other questions? And now let me move to what will be your favorite source of examples here, which is quivers. So a quiver is a directed graph, and if I want to be very pedantic, I'm going to say that this is this consists of two sets, finite sets. Q0 is a set of vertices, Q1 is a set of arrows, and H and T are maps from Q1 to Q0 where, well, we say that an arrow alpha starts at its tail and ends at its head. Okay? Now, fix two vectors, say v and w, to Q0 tuples of vectors with whose entries are positive integers. Well, thank you, non-negative integers. And well, we define space of co-frame representations of Q as follows in the next board. Well, I'm going to denote this by R for representations Q, V, W, and well, a representation of a quiver should be assign a vector space to each point and a linear map to each arrow. Okay? And when we have fixed the dimensions of those points, then, well, this is just the space of maps. So it's going to be the direct sum over all arrows. Well, this is just linear maps. C to the B tail of A, C to the B head of A. These are just numbers, okay? And well, if you work with quivers, then this is just a space of representations. But now we have to find a coframing, okay? This coframing is going to be, now we're going to assign a linear map going from V's to W's. Okay? Well, now this is the CVK to CWK. Okay? So, take for example, I don't know, an easy quiver.
Take the dot quiver.
Well, take the dot quiver. Okay? Actually, this is key. So here, V and W are just non-negative numbers.
So your V depends on the alphas.
Your V does not depend on the alphas. What depends on the alphas is, well, what is the dimension of its head and of its tail.
So you mean dimension?
Yeah. So, well, these guys are just numbers. Okay.
Yeah.
Remember that T of alpha is an element of Q0.
Yeah.
Okay. So this is just a vertex. So your V's depend on the vertices, so to speak.
Vt alpha is the dimension?
Is the, well, Vt alpha, remember that V is a tuple of numbers. Okay?
So, yeah.
Yes.
Yeah.
Which you're going to think as the dimension of the space
Right.
at
So the Q null.
yes, Q0.
Q null.
Yes. Yeah, Q naught. Yes.
Right? Okay. They were numbers.
Okay. Okay. So take the quiver with 1 point. Okay. So here V and W are just non-negative integers. Okay. And so, well, we don't have arrows, so this thing doesn't count. But we are going to have a map from CV to CW. Okay? So this space well is just going to be the set of matrices of times of size V times W. Okay? Any questions?
Take one loop.
Okay, now take one loop. So it's this guy, okay? And, well, now again B and W are numbers. So now this guy is, well, you have to take for each arrow alpha home from well, from the starting to the final point of the arrow, which in this case is the same, and now plus. And now okay, maybe this diagram will be helpful. So you have V here, now you go to W, and this box is because these are the framings, and it's going to be clearer in the next few minutes. Okay. Okay. So this is going to be our space X, where our group is acting. Now I have to tell you which group is acting, okay? So now let G be the product of GLBIs, well, BKs, better, over all vertices. Okay? So we are just taking the VKs. We're not taking W into account here.
So
okay?
K is this fixed vector space of dimension small, right?
Of dimension what?
So before you have like C to VK.
Yes.
And this is
So it's just like GLM.
yeah.
Yes.
There's a number there.
Yes. Yes. Yeah. Yeah.
That's a number.
Yeah. Yeah. VK is a number. I took the dimension vectors, not that. Yeah. Okay. And well, this guy is going to act on this set of confirmed representations as follows. So let's take G. Well, this is just a tuple of matrices, okay? And let's take an element here, which, well, this guy looks like, let me see, what notation did I use? Well, G alpha, and maybe I don't want to use G here.
So you're not using I and J and whatever, or X. Maybe it could be X.
Okay, yeah.
And then
X alpha.
And then YK.
YK. So remember that X alpha is a map from the head, from the tail to the head of alpha, and YK goes from C to the VK to C to the WK. Okay? So if I want to apply here to X, well, I'm going to conjugate this X alpha by, well, I have to take G to the, well, the head of alpha part of G. I keep writing A. Okay? And the way it affects K, well, again, this is like this. Okay? Should I give you some time to digest this? Or?
Yeah, we need to
So you just
So,
Well.
so what's the general plan? Does Jose continue after the break, or
Yes.
Aha. So then maybe, well, you want to give a definition. You can give the definition, and then we have the break.
Well, I'm not going to give a definition right now.
Ah.
I'm just going to give a couple of exercises, and then we have the break.
Okay.
Okay?
Yeah.
So let me give you a couple of exercises. Exercise 1. Well, we want to say when is the orbit of a point closed. The orbit of the point x alpha yk, we remember here alpha runs over the arrows and k over the vertices, is closed if and only if, well, first of all, yk is 0 for every k, and the representation of q determined by the x alphas is semi-simple. Okay, where maybe
there should be exercise 0.
well, that should depend whether the query has loops or not, and
so it's semi-simple even if you.
even if the query has loops, yeah.
So there should be exercise number 0 to say what is a direct sum of representations of a quiver without framing. But that's an
That's -1. You know that grading here starts from negative numbers? I mean, at the exam. So there are negative, so potentially there are negative grades at the exam.
something you cannot do in the United States. Right?
Okay, so exercise 0 is to make sense of what does this mean. Okay? And exercise 2. So first of all, let me tell you how characters of this group look like. So a map theta that goes from G to C times always has the form character. Thank you. Well, theta of this GK is the product of the determinant of GK to some number. Okay, where these guys are integers. So we are going to identify the set of characters with C to the Q0. Okay?
Z.
Yeah, C. Yeah. I mean, we Latin people have trouble distinguishing between this C and this C.
I didn't say that. You said that.
Yeah, I know. Now take such a character with only positive entries. Okay. Then co-framed representation x alpha yk is semi-stable with respect to this guy if and only if the only X alpha stable collection of subspaces in C to the pk. So you pick a subspace in C to the pk. Actually, sorry, I don't want it here. I want it in the kernel of my k. Okay? This is 0. Representation. So all these guys have to be 0.
So in particular, if they are embeddings, then
If they're embeddings, then you only take 0. Okay?
I mean, this is automatically guaranteed by yk being embedding.
Yes.
0 kernel.
Yes, yes, yes. Okay. So, for example, if again we take Q to be the quiver with only one vertex, then, well, our representation looks like that. Okay? G of this vertex, Y is semi-stable under the restriction that the coordinates are positive. If and only if Y is injective. Okay, so for this quiver, we have that R Q B W. Well, if we take the GIT quotient with respect to such a character with positive entries, well, this is going to be the Grassmannian of v-dimensional subspaces in C2W. If B is smaller than or equal W and empty otherwise. Okay.
So I think this example deserves the name exercise.
Okay.
And we have seen this in the case when v is equal to 1. When v is equal
Yes.
to 1, it's the example from the previous class.
Yes. When v is equal to 1, this is just, well, C to the n, well, C to the W, and you have the projection.
Okay, let's have the break.
Yes.
So how long break do you want to have? 15 minutes? 10 minutes?